All right, let's dive in. Today we're talking about computational graphs, the absolute blueprint of modern AI. This is the hidden architecture that lets AI systems learn from tons of data without, completely falling apart. It's the secret sauce in frameworks like TensorFlow, so let's break down how it all works.
So you've got these massive AI models, right? They're basically a crazy web of millions, sometimes billions of calculations all linked together. So the big question is, how on earth do they handle all that complexity without just getting hopelessly tangled up?
Well, here's the trick. They use a blueprint. And get this, if you've ever worked with relational databases, you're actually already halfway to understanding this. The logic is going to feel really familiar.
Okay, so let's get into this idea of a blueprint for calculation.
You know how a database schema is the blueprint for your data, right? It lays out all the tables, the columns, what kind of data goes where, and how everything is related. You define it once, and that's the law of the land for your data. A computational graph, it's the exact same concept, but for math. It's a blueprint that defines every single calculation, every variable, and how they all connect before anything actually gets computed.
So what are these blueprints actually made of? Well, like any good plan, they're built from some basic building blocks. We call them nodes.
You can think of a node as a fundamental unit in the graph. It can be a value, like a variable or a constant, or it can be an operation, an action, like adding or multiplying. Let's dig into the main types.
First, you've got variables. These are the parts of the model that can actually change. Think of them as the adjustable knobs. They hold the values, like the weights in a neural network, that get tweaked and updated during training. This is basically where the learning part happens.
Then there are constants. And yeah, they're exactly what they sound like. Their value never, ever changes. You set it once when you're building the graph, and it's locked in. Done.
And finally, there's a really important one, especially in older TensorFlow code, the placeholder. A placeholder is basically a promise. It's an empty slot in your blueprint where you say, hey, I promise I'm going to feed some data in right here when it's time to run the calculations. This is typically how you'd get your input data into the graph.
Okay, now this next part is maybe the most important concept to grasp. It's this idea of a two-phase system. This is what makes the whole thing so powerful. There's this quote that really just says it all. In TensorFlow, you first must create a computational graph, then create a session, and finally run your graph. See? It's a strict two-step process. You build the thing, then you run the thing.
So step one is all about defining that blueprint. You're laying out all your variables, your operations, how everything connects. But, and this is the key, nothing is being calculated yet. Zero. You're just drawing the map. It's not until step two, the execution phase, that any actual math happens.
Let's look at what this actually means in code. On the left, in the construction phase, we're defining two variables and then an operation to add them together. Now, at this point, that z operation doesn't have a value. It's not 3. It's just a node in our graph that represents addition. Then look to the right in the evaluation phase. To get the actual number, we have to create a session and then explicitly tell it to run the z operation. Only then does the computer actually do the addition and give us back the answer.
So how do we bring that blueprint to life and actually get an answer? This is where that database analogy becomes super useful again, as we talk about something called a session.
Think about it. Your database schema just sits there, right? It's a static blueprint. It doesn't do anything until you run an SQL query against it. That query is the action that actually makes stuff happen. Well, a TensorFlow session is the exact same thing for your computational graph. The graph is the blueprint, the session is the action that executes it.
A session is basically the environment where the magic happens. It's the bridge between your abstract graph and the actual hardware, like your CPU or GPU. When you tell a session to run, you're essentially saying, okay, take this plan we made, send it over to the processors, and bring me back the results.
So why is this system so genius? I mean, you might be thinking, this sounds kind of complicated. Why not just do the math right away? Well, it turns out this separation between defining and executing is the secret to making these frameworks so incredibly fast and powerful.
Because the framework gets to see the entire blueprint of calculations up front, it can do some pretty amazing things. It can optimize the whole process, figuring out the smartest way to do the math. It can spot calculations that don't depend on each other and run them at the same time, in parallel, which saves a ton of time. And since the graph is just an abstract blueprint, you can run it anywhere, from a huge server cluster to your phone. That combo of optimization, parallelism, and portability, that's the real genius here.
So you see, the computational graph isn't just some nerdy technical detail. It's the very foundation that makes modern AI possible at the scale we see today. It's the master plan. So, now that we have the blueprint, what are we going to build with it?
And that's the whole idea behind computational graphs. If you found this explainer helpful, hey, do us a favor and hit that like button, share it, and subscribe for more. We'd really appreciate it. Thanks for tuning in.